Okay, let's talk about something really interesting in quantum mechanics. It's called the no-cloning theorem. It sounds a bit like science fiction, maybe like someone trying to copy a person, but it's about information, very tiny bits of information. And it tells us something fundamental about how the universe works at its smallest scales. So, what is it? Simply put, the no-cloning theorem says you cannot make a perfect copy of an unknown quantum state. Not ever. It's impossible. If you have a quantum particle like an electron or a photon and it's in some specific quantum state, its own unique fingerprint, its own combination of properties, you cannot just scan it and print out an identical perfect twin. You can't duplicate it perfectly without destroying the original or at least changing it in some way. Think about it like this. Imagine you have a mystery coin. You don't know if it's heads or tails. But it's a special coin, a quantum coin. It might even be both heads and tails at the same time in a kind of blurred way. The no-cloning theorem says you can't just magically create another identical mystery coin that's also in that exact same blurred state of heads and tails without first finding out what the original coin was doing, which would then make it pick one state, heads or tails, and lose its blurred nature. You can't peek at it, copy it, and put the original back without anyone knowing you looked. That's the core idea. This isn't just some technical detail, it's a huge deal. It changes how we think about information itself. In our everyday world, with regular computers, we copy things all the time. You copy a file on your hard drive. You copy a picture on your phone. You can copy a key. You can copy a document. This is easy. You just read the information, then write that same information somewhere else. And the original stays exactly as it was. That quantum information, the kind that lives in quantum particles, doesn't work that way. To really get why this is such a big deal, we need to talk a little bit about what a quantum state actually is. Don't worry, we'll keep it simple. In our normal world, things have definite properties. Right? A ball is either red or blue. It's either here or there. It's either spinning clockwise or counterclockwise. These are definite specific states. But in the quantum world, things get weird. Particles can exist in something called a superposition. This means a particle can be in several states at the same time. It can be red and blue at the same time, or spinning clockwise and counterclockwise at the same time. It's not that we just don't know which one it is. It really is in both states at once, in a kind of blend. Imagine that quantum coin again. Instead of being just heads or just tails, it can be a mix of both. Maybe 70% heads and 30% tails, or 50-50, or whatever. It's a spectrum of possibilities. This mixture, this blend of possibilities, that's what a quantum state can be. When we actually look at the coin, when we measure it, it has to choose one state. It collapses out of its superposition and becomes either heads or tails, and that measurement changes its state. It's no longer a blend, it's now definite. So if you have a particle in one of these fuzzy blended states and you want to copy it, what do? If you try to measure it to find out its exact blend, you force it to pick a definite state. Then you've lost the original blend, you've changed the original, so you can't just read it like you read a classical file. And if you try to make a copy without measuring it, without knowing its exact state, that's where the no-cloning theorem steps in and says, nope, impossible. Let's think about why it's impossible. The proof of the no-cloning theorem isn't super complicated mathematically, but we can talk about the idea behind it without any math at all. It relies on two main ideas that are fundamental to how quantum mechanics works. The first idea is that quantum operations are linear. What does linear mean here? It means that if you have a process, a machine, or an interaction that takes a quantum state and transforms it, then if you put in a combination of states, you get out a combination of the transformed states. It's like if you have a blender that turns apples into applesauce and oranges into orange juice. If you put in a mix of apples and oranges, you get a mix of applesauce and orange juice. You don't get apple-orange smoothie. It keeps the proportions. The second idea is that quantum operations must be unitary. This sounds fancy, but it just means that quantum processes conserve information. They don't lose information, and they don't create it out of nothing. It's like a rotation. If you rotate an object, it's still the same object. It just looks different from a new angle. And its total amount or size hasn't changed. In quantum mechanics, this means that the probabilities associated with all the possible states always add up to 1. You can't just have a particle disappear, and you can't have two particles suddenly appear from one without some other part of the system changing. Okay, now let's imagine we could build a cloning machine. Let's call it the quantum duplicator. We feed it one quantum particle in an unknown state, and it spits out two identical particles in that exact same unknown state. And it does this perfectly every time for any state we give it. Let's say we have a particle, it could be in state A or state B or a superposition of A and B. A superposition is like saying it's part A and part B at the same time. So, if our cloning machine works, it should do this one. If we put in a particle in state A, it should spit out two particles, both in state A. Now, here's the kicker. What if we put in a particle that's in a superposition of A and B? Something like half A and half B at the same time. What should the cloning machine do according to our assumption? Well, if it's a perfect cloner, it should create two copies, each in that exact same half A and half B superposition. So we'd end up with two particles, and each of them would be half A and half B. But remember the linearity principle? Because quantum operations are linear, if the input is a superposition half A plus half B, then the output must be a superposition of the outputs for A and B separately. So, if we put in half A plus half B, the linear cloner would give us half A plus half B plus B. This means we'd get one particle in state A and one in state B, but still linked by that superposition. Not two copies of the original superposition. This is the crucial point where it breaks down. The output of a linear process operating on a superposition is fundamentally different from two independent copies of that superposition. Let's try to make that even clearer. Imagine our quantum cloner, C, takes a particle and copies it. So state A should give us state A, and state B should give us state B. Now, what if we give it a superposition SE state A plus state B squirt 2? The SE squirt 2 just keeps the probabilities adding up to 1. A perfect cloner would give us SEA A plus B square 2, A plus B square 2. This means we have two copies, and each copy is individually in that A plus B superposition. But because quantum operations are linear, the cloner operating on S should give us CA plus squirt 2. By linearity, this must be CA plus CB squared 2, and since CAA, AAA, and CB, BB, this means the output is AA plus BB squared 2. Now, compare these two outputs. 1. What a perfect cloner should give A plus B squared 2, A plus B squared 2. In the first case, you have two particles, and each one separately is a mix of A and B. In the second case, you have a single combined state of two particles. This combined state is a mix where either both particles are A or both particles are B. They are linked. This is what we call entanglement. This means that a linear quantum operation, which is what all quantum processes are, cannot produce two independent, identical copies of an unknown superposition state. Instead, it would create an entangled state where the two copies are linked in a way that doesn't match two independent copies of the original. This is the contradiction. It means a perfect quantum cloning machine is impossible. And it's not just superpositions that are a problem. It's any pair of non-orthogonal states. Without getting too technical, non-orthogonal states are basically any states that aren't completely distinct from each other. If two states are orthogonal, it means they are perfectly distinguishable, like a vertical polarization versus a horizontal polarization for a photon. If you have a known state, say you know it's definitely vertical polarization, you can create another vertical polarization photon. But if you have an unknown state that could be vertical, horizontal, or somewhere in between a diagonal polarization, you cannot clone that unknown diagonal polarization perfectly. So, the No-Cloning Theorem tells us that this fundamental rule of physics prevents perfect duplication of an unknown quantum state. It's not about our technology not being good enough yet, it's a hard limit set by the laws of quantum mechanics. Why does this matter beyond being a cool theoretical idea? Well, it has huge practical consequences, especially for something called quantum cryptography and the future of quantum computing. Let's talk about quantum cryptography first. This is about making truly secure communication. You know how we use encryption keys to scramble messages? If someone gets the key, they can read the message. So, protecting the key is everything. With regular classical keys, if someone manages to intercept the key, they can make a copy of it and then let the original continue on its way. You, the sender, and the receiver would never know your key was compromised. The eavesdropper now has a copy of the key and can read all your messages. But with quantum cryptography, we can use the No-Cloning Theorem to make a key that is truly tamper-proof. The most famous example is something called BB84, developed by Charles Bennett and Gilles Broussard. The idea is that the key is made of a sequence of quantum states, often photons. If an eavesdropper tries to intercept these quantum key bits, these photons in specific quantum states, they have a problem. They can't just make a copy of each photon state and send the copy along, because the No-Cloning Theorem says they can't make a perfect copy of an unknown quantum state. To even try to figure out what state the photon is in, they have to measure it, and as we discussed, measuring a quantum state collapses its superposition and changes it. So, If an eavesdropper tries to measure the photons to learn the key, they will inevitably disturb the states of those photons. When the sender and receiver later compare a small sample of their shared key, they will notice these disturbances. The error rate will be too high. This tells them that someone has been listening in. Then they can just discard that key and try again. The security isn't based on how hard it is to crack a code, it's based on the fundamental laws of physics. The act of observation is detectable. That's incredibly powerful. It offers a level of security that classical cryptography simply can't match. Now, what about quantum computing? Quantum computers use kits instead of classical bits. A classical bit is either a 0 or a 1. A qubit, because of superposition, can be 0, 1, or a combination of both 0 and 1 at the same time. This is where a lot of the power of quantum computing comes from. The no-cloning theorem has big implications here. In a classical computer, if you need another copy of a bit of information, you just copy it. If you need to store the result of a calculation in 2 different places, you copy it. It's a fundamental operation, but in a quantum computer, you can't just copy a qubit. If you have a qubit in a certain state and you want another qubit to be in that exact same state, you can't just press C V. This means that you can't duplicate quantum information at will. This affects how quantum algorithms are designed. You can't just back up a qubit state or make multiple identical inputs to parallel processes in the same way you would with classical bits. Does this mean quantum computers are severely limited? Not necessarily. It just means the rules are different. While you can't perfectly copy an unknown quantum state, you can do other things. For example, you can swap quantum states. Imagine you have a qubit A in some state and an empty blank qubit B. You can perform an operation that transfers the state of A to B, and A becomes blank. This isn't cloning A, it's moving. The original is gone from its first spot, but now B has its state. You can also create entangled qubits, which are linked in a special way, but they aren't independent copies. You can also make copies of known quantum states. If you know for sure that a qubit is in state 0, a definite 0, not a superposition, you can prepare another qubit in state 0. That's not cloning an unknown state, that's just preparing multiple identical items from scratch, knowing exactly what they should be. It's like having a recipe and making 2 identical cakes. It's not like taking a mystery cake and instantly replicating it without knowing the ingredients. So, the no-cloning theorem is a constraint, a fundamental limit. But quantum computer scientists and engineers work within these limits. They design algorithms and hardware that respect these rules. It's a bit like an architect designing a building under the laws of gravity. The gravity is a constraint, but it doesn't stop buildings from being built, it just means you have to design them properly. This theorem really tells us something profound about the nature of information in the universe. Classical information is robust. It can be copied easily. Quantum information is fragile and unique. It resists duplication. It's inherently linked to the specific physical system that carries it. This non-duplicability is what gives quantum mechanics many of its unique and often counterintuitive properties. The no-cloning theorem was first articulated in the early 1980s by physicists like Dennis Deeks and independently by William Waters and Wojciech Zurek. It wasn't some grand revelation. It arose from careful consideration of the mathematical structure of quantum mechanics and what operations were allowed within it. They essentially showed that any attempt to construct a perfect universal cloning machine would violate the fundamental linearity and unitarity of quantum mechanics. Think about what it would mean if we could clone quantum states. For one, it would break quantum cryptography completely. If an eavesdropper could just clone the photons, they could read the key without detection. Security would vanish. It would also lead to some strange paradoxes related to entanglement. Entanglement is when 2 or more particles become linked so closely that measuring one instantly affects the other, no matter how far apart they are. It seems like it could allow for faster than light communication, but another theorem, the no communication theorem, says that it doesn't. If you could clone, you might be able to find ways around that. But because you can't use entanglement to send messages faster than light. The no-cloning theorem is one of the pillars that uphold the consistency of quantum mechanics and its compatibility with special relativity. Consider its philosophical implications too. It suggests a deep uniqueness to quantum states. Each quantum state is, in a very real sense, singular. It cannot be perfectly replicated without either altering the original or knowing the original's precise blueprint beforehand. This uniqueness is a hallmark of quantum reality. It highlights that quantum information is not just a different kind of information storage, it fundamentally operates under different rules than classical information. So, to wrap it all up, the no-cloning theorem is a fundamental principle of quantum mechanics. It states that you cannot perfectly duplicate an arbitrary, unknown quantum state. This isn't a limitation of our current technology, it's a hard rule of the universe. It comes from the linear and unitary nature of quantum operations. This theorem is crucial for understanding the security of quantum cryptography, where it guarantees that eavesdropping is detectable. It also shapes the design and limitations of quantum computers, reminding us that quantum information behaves very differently from the classical bits we're used to copying so easily. It tells us that at the smallest scales, information is much more profound and unique than we might have imagined. It's one of those beautiful, strange ideas that makes quantum physics so endlessly fascinating.